Welcome back, Physical Science. This is the 16.3 thermochemical equations section, and this fits into the HT2 part. So there's only one page here, notes, and a quick assignment here. Talking about thermochemical equations, of course we talked about exothermic reactions release energy, and endothermic reactions absorb energy, and referred to this as delta H, change in enthalpy. And it can be in the equation or outside of the equation. So if we look over here, thermochemical equation is a balanced chemical equation that includes the physical states of all reactants and products, and the energy change usually expressed off to the side as a delta H. So by looking at this is from yesterday, or from the other video, delta H equals negative. That implies automatically that it's an exothermic reaction. So if I was to have it inside the equation, of course it'd be on the right-hand side, the product side, because it's produced. And delta H equals positive 27. With it being positive, that tells us automatically that it is a reactant, because we need to add it into the system to make the reaction happen. Okay, the next part here, so we have enthalpy of just the reaction. If we can confine it to a particular type of enthalpy, or energy released or absorbed, we can talk about the enthalpy of combustion. The enthalpy of combustion, symbolized delta H with a COMB, short for combustion, is the enthalpy change or the energy change for the complete burning or combustion of 1 mole of substance. And of course we could look at common enthalpies here on this table. So sucrose, we can see it involves a lot of energy actually. Sugar tends to be a little messy though, so that's why we're not using that in our combustion engines. Octane, glucose, propane, etc. You can see that, and you can see the more complicated the molecule is, bonds are broken. We can get more energy from more bonds. So H2 negative 286, whereas sucrose is that. So, and that kind of lends itself to a combustion lab that we'll be doing very soon. Okay. If I look at a couple of examples just dealing with enthalpy of combustion, we'll look at, first of all, if I'm given a certain mass of a compound, how much energy is involved, and then vice versa to that. So you can just copy this out on loose leaf. Determine the amount of thermal energy released in the combustion of 5 grams of ethanol. So of course ethanol, if you don't know what that is, right here, ethanol C2H5OH. So we need to know that. And also looking back here, we know the enthalpy of combustion of ethanol is negative 1367 kilojoules per mole, per 1 mole. So that's where this comes from. So our method here, our plan of attack, we're given grams. We know how much energy is released per mole. So if we can convert our 5 grams into moles, then we can use the enthalpy of combustion to go from moles to kilojoules. So, of course, in order to go from grams to moles, we need to know the molar mass. So the molar mass of ethanol, C2H5OH, 2 carbons, 5 plus 1, that's 6 hydrogens, 1 oxygen. So, of course, looking up the values on the periodic table, going at least 2 decimal places, 46.08 grams per mole. So, grams to moles, moles to kilojoules, so we could just set it up in 2 easy steps. So doing the molar mass conversion, grams to moles, as illustrated here, grams to moles, we will change our 5 grams into moles, and then from moles to kilojoules, as outlined, the enthalpy of combustion was negative 1,367 kilojoules per 1 mole. So grams cancel, moles cancel, and left with 148.3289931 kilojoules to the negative, rounded off to 3 sig figs because my original number was 5.00 grams, and I get negative 148 kilojoules. And of course the negative implies that it's exothermic. Combustion involves the release of heat. Another question, vice versa though this time. What mass of propane is required to release negative 543 kilojoules of thermal energy? Okay, so if we look back here, propane first of all is C3H8, involves the release of negative 2219 kilojoules per mole. So write that information down. The enthalpy of combustion, negative 2219 kilojoules per mole. So the rationale here, I want to find grams. I'm given kilojoules, and of course I have a relationship here between energy and amount. So kilojoules to mole will be my first step, and then of course the molar mass, I'll use that to change it back into grams. So the molar mass of propane, 3 carbons, 8 H's, 44.11 grams per mole. And then setting it up, negative 543 kilojoules. And of course in my little red scheme here, going from kilojoules to mole, using the enthalpy of combustion. And then from moles to gram, 10.79392 grams, or rounding it off to 10.8 Gs. Okay, so that deals with combustion, enthalpy of combustion, thermochemical equations. The assignment I want you to do and hand in is over here. A couple of things you can add. So first of all, number 1, list the information contained in a thermochemical equation. You'll be able to easily find that back here. The next 2 questions involve what we just looked at with the practice questions, and I've given you a little hint here. Number 2 is like practice question number 2. Number 3 is like practice question number 1. So we're starting off with joules, going to grams, and then grams to kilojoules. A little hint here, releasing 12,880 joules. That's the same thing as negative. And also changing that to kilojoules, because that has to be in kilojoules since my enthalpy of combustion is in kilojoules. And here methane, yes, is CH4, hydrogen, H2, etc. Number 4, how much energy is involved in dissolving sodium hydroxide in water? The table shows data from an experiment in which a measured amount of NaOH is dissolved in water in a foam cup calorimeter. Calculate the enthalpy for the process in kilojoules per mole. If the enthalpy change for the solution of NaOH is known to be this, what percent error is the experiment? So we know our answer is going to be close to this, hopefully. So if you get an answer that's way far away from this, something is wrong. So some pieces of information here, mass of sodium hydroxide in weighing paper, and the mass of weighing paper, so you know you can just simply subtract here and get the mass of sodium hydroxide. Mass of foam cup and water, and I think yours is the updated version of this, so I think you do have this part here that says the mass of the empty foam cup, 10.25 Gs. So of course subtract that, we get water. And then the initial temperature of water was 25.5, and the water increased in temperature because sodium hydroxide transferred heat to it as it dissolved. So we get our change in temperature. Hints, very similar to a previous calculation that we did, determined the heat transferred to the water. So the Q water plus the Q of NaOH should all add up to be 0, as opposed to a sideways shocking face there. That's all I see now. So Q water, MC delta T, like we did before, the specific heat of liquid water, 4.184 joules per gram degree C. My Q of my heat of NaOH. So what happens here, of course, is all the heat from the NaOH goes to heating up the water. So I'll just leave this as Q, because I want to figure out the energy involved. I know mass of water, specific heat capacity of water, temperature change of water, and I'll simply put this all in, rearrange, solve for Q, and I'll get my Q value in joules. But, of course, I want kilojoules per mole, so if I can slowly get to that by first taking my joules divided by my mass of NaOH that I figured out up here, my unit will be joules per gram, but of course I want kilojoules per mole, so that'll lead just a couple of conversions as you see on the next page. Take my answer that I had from the previous page, convert from joules to kilojoules by dividing by 1,000, and then changing grams into moles by multiplying by the molar mass here, and my answer will be in kilojoules per mole. And a hint, again, should be very close to this negative 44.51. Then to figure out the percent error, my observed value, whatever I get over here, minus the actual divided by the actual. So this is the actual value it should be, but what did I observe in my experiment? That's what I'm figuring out. All right, So this is the second assignment in the HT2 booklet. We'll see you again.